So my talk today is devoted to dynamics of topological defects in polariton quantum fluids. But I think that the evening of the first day of the conference is a good time to some general introduction to polaritons with the focus on semiconductor microcavity polaritons and with extreme stress on the resonant pumping scheme. And after this introduction, still I believe that the students and young postdocs are here, as well as some IBS members whose topic is not very focused on polaritons. So I will do this introduction, and after it, I will go to the third part of talk devoted to solitons confined in the 1D channel with optically pumped walls. I will show that in such configuration we can observe the soliton snake instability and then freeze it and detect it in CV experiment. And I will also say that such experimental scheme can serve to can serve for the analog of maze solving algorithm by dead end stroking. Then short mention about solitons in supersonic flow, and after that's it about the solitons, and then I will go to quantum turbulence. First about the conservative case, about I will say about incompressible kinetic energy spectra and how they are related to fractal structures of vortices. And finally, I will go to prediction of a turbulent and high angular momentum state in spinor in the polariton quantum fluids with spin orbit coupling of TTM type. So let us start. So polaritons are composite particles made due to interaction of photons and excitons. And here I show you the semiconductor microcavity, where we have some photonic mode in between the distributed Bragg reflectors. So this is the cavity photon mode, first ingredient to form the polariton. And the features of cavity photons are lifetimes of dozens of picoseconds due to progress in manufacturing the mirrors. And what is also important is that for the in-plane wave vector, we have parabolic dispersion. In fact, we have the Taylor expansion of dispersion for small in-plane wave vector, in other words, for small detection angles, and the obtained mass of photon is of the order of 10 to the power minus 5 of the order of electron. And overall, this is very closely related to paraxial approximations, and we can rewrite the Maxwell equation from Maxwell equation for electric field in the microcavity with its geometry to the Schrödinger equation like equation. And we plug into this equation losses due to radiative losses of photons, and also we can put here the resonant laser pump. It just acts as a electric field of the laser. And what is important by this term, by resonant laser pump, the wave function in the microcavity can be shaped by laser. Shaped, I mean we can control its amplitude and phase. The second component for formation the polariton is the exciton, which lives in the quantum well in between the Bragg mirrors, and one can write this Hamiltonian of interaction between excitons and photons. And if the condition of strong coupling regime is satisfied, it means that the polariton is formed, and in dispersion it's visible as anti-crossing and formation of upper and lower polariton branches. And physically, this condition means that the polariton has enough time to make a lot of oscillations between excitonic and photonic components. And returning to the Maxwell equation for photon, or to Schrödinger equation, we can now substitute this repulsion term due to excitonic interaction, and also interaction with excitons renormalizes mass of polariton by the factor 2 with respect to mass of photon, and also it renormalizes by factor 2 approximately 2 the decay rate of the polariton. So what will be very important for the story on solitons? It is resonant pumping regime and the phenomenon of bistability. So imagine that we are starting from zero intensity of laser, and we are gradually increasing the intensity. So let us we are driving somewhere above the cavity photon mode. So by the laser pumping leads to increasing of density of polaritons, and it leads in blue shift of the energy of mode, and as a result, the pumping we come closer to resonance, and pumping becomes more efficient, and so on and so on. And once we reach some point, we have some abrupt jump in intensity. We are now acting in resonance. And what happens with the phases of in such procedure? So while we are going while we are going up in the laser intensity, we are following this curve of psi square, of density of polaritons, and the phase is going like here. So when we are at the bottom branch of bistability, we are in phase with laser. We are acting in linear regime. But once we jump to the upper bistability branch, we start acting in the anti-phase with laser. And then if we go back from high densities to lower densities, we do not follow the previous path in intensity and in density and in phase. So we go around some hysteresis loop or bistability loop, and the same is the phase. And from this slide, what I would like to stress is that if the laser is acting somewhere within the bistability loop, it allows rich phase behavior. And it is essential condition to observe the topological defects like solitons or vortices, which by their nature imply abrupt jumps of the phase. So, and now let us go to the part on solitons and their modulational instability. And here, one more preparatory slide. Consider the following experimental configuration. We have some weaker resonance support falling somewhere within the bistability loop, somewhere here. But if we have a lone support, we will not be able to drive the system to the upper bistability branch, because we will remain here. But if we somewhere locally in space we add pump, this pump can locally drive the system to the upper bistability branch with higher density. And imagine that at some time moment we have two domains in space, at the high bistability, at the upper bistability branch, and at lower stability branch with low density. In this case, depending on the value of support, this domain wall between these two regions can be stable or move left or right. It depends on the value of support. So we can find by considering some minimal action for the Gross-Vitaevsky equation, we can find some critical support where this domain wall is not moving, and also in the vicinity of this critical support, the domain wall is linear in the value of support. So if support is higher than critical, the domain wall moves right, and otherwise at lower supports it moves to the left. So further, we will operate about the intensity of laser in the terms of values of critical support. And yes, this is piece of art. This is some red square, and it shows the illumination radiation configuration that we will consider in the next part of talk. This is homogeneous support and channel formed and optical channel formed of walls under intensive pump. So if we start with this configuration and run the simulation, we will obtain the following. So two pair of solitons, and why these two guys are real solitons? Because if we apply somewhere some instant perturbation, pick the wave function by some potential, just instant action on this, it will switch on the modulational instability, and as a result, the solitons will transform to the street of vortex and antivortex pairs. So this configuration is unstable, and by linearization by Bogolyubov method, or writing the Bogolyubov-Dejean equation, we can analyze the stability of such configuration, and it was done. And in general, this plot shows the imaginary part of the Bogolon as a function of wave vector along y-axis. And the Bogolon with the highest imaginary part grows most rapidly, and this arc and this mode of Bogolons corresponds to antisymmetric pattern. If we change somehow the values of the pump at the walls and support everywhere, we can obtain that the more favorable is formation of symmetric pattern. And we can plot the phase diagram of the behavior of this system in the following coordinates. Support in the units of critical support where the main wall stands, and pump plus support over S. So pump plus support is the level of laser at the walls. So at most number of parameters, we have formation of symmetric patterns from the solitons to vortex-antivortex pairs, and at some parameters we have formation of antisymmetric, and also there exists the parameters where the solitons have the behavior of oscillation, like the parts of accordion, like this. So this configuration is varying in time. It is not stable, and the same can be obtained by applying the direct disorder to the system. So here we have the disorder in the potential. It more or less corresponds to the disorder in the energy of polaritons, potential energy of polaritons in the microcavity, And this phase diagram matches very well with the previously shown phase diagram based on the Bogoliubov-Dejan equation, where we can observe the antisymmetric snake-like patterns with high values of the soliton center mass deviation from the center, and these symmetric configurations then corresponds to nearly zero value of center mass of the solitons. So this part of presented results is very tightly connected with the paper by Jacqueline Bloch and Alberto Ama group. Where the authors were investigating the one-dimensional elongated wire-like microcavity with the two pumping spots at the ends. So in fact, this experimental configuration is the cross-section of my channel from previous slides. And so, depending on the phase difference between the spots of the laser, they were observing even or odd number of solitons. In the same manner, if we apply the phase difference between the channel walls, we will obtain odd or even number of solitons by demand evolving to specific patterns of vortex and antivortex. So another important property of the proposed configuration is the realization of the dead-end stroking algorithm for more complicated geometry of the corridor. So here this dead end, it violates the translational invariance of the system, like here, and this perturbation switches on the formation of a modulational instability, like you see, and then by increasing the support intensity and driving it into the regime of a limit cycle, this head of the solitons start repelling from the dead ends, and so this maze is automatically solved. So this is a previous slide shows some small examples. This is much bigger example of 1 millimeter in size. So it is done. And the predictions from previous slides were justified by a group of Alberto Bramati in Université Sorbonne. So they were using very emerging microcavity dated from maybe 90s or beginning of 2000 years. So, but still it was sufficient to realize this experimental scheme. And by using they shaped the corridor walls by the usage of special light modulator, precisely using the first order of diffraction, and they observed the symmetric patterns, which is in agree with the phase diagram, where it is said that symmetric patterns are much more favorable to observe than antisymmetric ones. And they also observed the solution of the maze even more simple than the previous slide. And also this this channel of the sophisticated shape is filled by the vortex-antivortex streets formed from the solitons in the same manner as in the calculations. Here I would also like to demonstrate one other configuration where the solitons can be observed and studied in polariton quantum fluids. We again use the pump and support scheme. We have some big spot of support everywhere. It is not very intensive. It is falling within the loop, and we have local intensive pump here. So, but now we illuminate the cavity under some angle, which gives to the quantum fluids some momentum, and the corresponding velocity is larger than sound velocity. We are acting in supersonic regime, and we observe the following. We observe the pair of straight solitons which are propagated at high distance. So utilization of support changes the rules in this game, because normally if we use only pump to observe the solitons, we normally have the oblique solitons which cannot propagate at long distances. And another difference is that these solitons are gray because they are moving, because due to the fact that we have supersonic flow, the y coordinate efficiently becomes the time coordinate. So this is x coordinate, and this is time due to supersonic flow. And these solitons are black solitons. That they are deep. They are deep, guys. And now we go to the second part of the talk. To the second part of the talk devoted to studies of quantum turbulence and utilization of Exciton-Polaritons as the system to study quantum turbulence. So the following questions are open for the studies of two-dimensional quantum turbulence. If we have energy cascade or this Kolmogorov exponent, because in 3D turbulence we inject the energy at some large scales, and then this large scale fluid motion goes to lower and lower and lower scales up to the very small scale where the energy is dissipated. So the question is about existence of similar cascade in 2D and about applicability of the polaritons to study, to somehow contribute to the field of quantum turbulence. And here we study the conservative. We study the conservative case without any losses. So to deal with quantum turbulence, we must firstly somehow steer the quantum fluid, and now we do it by moving potential. So this is rather famous in the community of quantum turbulence, analog of rotating spoon excitation of quantum turbulence. And after some time of evolution, we have normally the following distribution of phase in the quantum fluid with multiple vortices and anti-vortices. Just by taking the wave function and plotting the velocity field, we can plot the incompressible kinetical energy spectrum here in red dots. But also we can plot the same only by the knowledge of the positions F and of the signs of vortices. And this is called analytical procedure, and one sees that if the results of numerical and analytical procedures correspond. But then we can remove isolated vortices or vortex-antivortex pairs, and only some larger hierarchical structures of vortices remain, some clusters of vortices. And if we calculate the kinetic energy spectrum only for clustered vortices, we can locally see the power law which corresponds, which matches with the Kolmogorov exponent. And noteworthy, the signal for uncleaned from single vortices wave function, it is just k to the power -1. The following exponent says about the dominance of the signal from signal vortex. So this is more or less spectrum of a signal vortex. And also we have analyzed the fractal structure of the vortex clusters in such a system. We have calculated the Minkowski dispersion by varying the number of boxes covering the manifold and tracing the number of boxes of these boxes required to cover all manifold. And we can see that in the place where we have transition from two-dimensional to zero-dimensional regime in a fractal dimension, so this place matches with the place where we have Kolmogorov-like exponent. And also we have traced the time dynamics of distribution of energy of the quantum fluid during the steering. And one sees the transfer of energy from low wave vector to highest wave vector during time. And here I would like to finish my talk today with the configuration of excitation of turbulent-like and high angular momentum state in the system with spin-orbit coupling, in defective spin-orbit coupling caused by TTM splitting. Here are the equation governing the dynamics of wave function of two components, sigma plus and sigma minus polarization. And in this scheme, we were pumping recently pumping one of the component, let's say sigma plus component, and we were looking to what happens in the second component, and these are densities in the sigma plus and sigma minus. And in sigma minus, the numerous vortices can be detected. And if we plot phase, so we will see in the middle a lot of vortices, and number of left and right vortices does not match. So, and it is also visible in the presence of some global rotation at the border of round of a circular cavity that we are considering. And if we consider the stability of the quantum fluid in the sigma plus component, we will see that the instability at some region and the domains of the the domains with such a wave vector start appearing in the second component, in sigma minus component, which finally develops to such turbulent-like structure with a high angular momentum. Practically, this can be detected by the self-interference experiment with self-interference with some point, and these interference fringes correspond to the typical value of wave vector around this trajectory, or by just local measuring the dispersion. So to conclude, the following was done. So we have proposed the configuration of the optical channel where the modulational instability of solitons can be frozen and the developed pattern can be detected in a continuous experiment, and it was justified in real experiment. So we also demonstrated the maze solving property of such a system by the soliton head repulsion from the dead end and realization of the dead stroking algorithm. And in quantum turbulence, to see some energy cascade, we need to remove the contribution of a single vortices and vortex-antivortex pairs. So from this point, the polaritons is good system because we can reconstruct the wave function of the system. But the very serious obstacle is that we need some screenshot of wave function, and this making the screenshot instant detection of wave function, it is not trivial. And all turbulent phenomena are not reproducible, so we cannot repeat the experiment to accumulate the signal. It is also a problem. But in conservative case, the Kolmogorov exponent in incompressible kinetic energy spectrum is associated with the fractal structures of vortex clusters. And finally, we have studied the configuration in the round cavity with TTM splitting to pump one of the component and to observe high angular momentum in the second one, and also the turbulent state, the fingerprints of the turbulent state in the second component are visible. So I would like to thank the organizers for giving the possibility to have a talk, and I also I'm indebtful to my colleagues from France, from the experimentalists in the group of Alberto Bramati, who worked on our ideas on the solitons, and to Guillaume Alpesh and Dmitry Solnishkov from Clermont-Ferrand. We worked on this stuff together. And thanks for attention.
Questions? Please.
You mentioned the superfluid or supersonic fluid in your talk, and I just wonder that is how your approach can be applicable here, because the supersonic flow usually violates some our conditions for existence, for even for existence of this superfluid. Is it
Well, anyway, these configurations are not pure condensates as they are, because we are acting in a driven dissipative regime. Well, here I say about quantum fluid. Just for me, it is synonym of it's the same meaning as that we are using not the Schrödinger equation for description of polaritons, but we are using the instead we are using the Gross-Pitayevsky equation with the repulsion term. So here we do not destroy the superfluid in some sense.
Questions? Yes.
So earlier this year, there came work from the Lecce group, Dario Ballerini and Daniele Insabito. They created a massive optical track, and they sent in resonant pulses to create this polariton fluid, and they reported evidence on polariton turbulence. So I don't know if they extracted the Kolmogorov exponent, but maybe you didn't mention their work, so I'm wondering, or was there something different about their experiment to what you were studying here? Or
I must look to the mentioned work with a certain attention, of course. Well, what is the main result from their work?
The main result is that they measured the compressible and the incompressible parts of their polariton fluid. And to that, they were able to get some results that evidence quantum turbulence. I don't remember exactly.
Mm-hmm.
I was just wondering if this was a topic on a few conferences. I was just wondering if there was any difference here to what you were showing about the Kolmogorov experiment and what they were reporting.
Well, I repeat that I must look with a very serious attention to this paper, and for me it really seems strange that it is simple to extract the contribution of the evidence of turbulence just by measuring the spectrum, because really in most cases of the excitation, because here we studied numerous schemes of excitation. In all schemes the contribution from the single vortices were dominating. So this claim seems to me strange, and I must check it. Thank you.
So in the first parts of your talk, when you showed us this phase diagram, seems like it always has this symmetry or anti-symmetric phase. But it seems like if you have like or when it's pumping, you should have like a uniform phase.
Well, just at lower values of pump and support, we just have no solitons initially. So here we are starting with a relatively high value of pump.
Oh, it's not okay. Sorry.
No, well, it's not. This axis is done not very nice. So we start from 1 here.
You have a question?
Yeah,
Please.
I have a question about the Polariton condensate flowing against an obstacle. As far as yes, this one. It looks like we have a formation of a bound state of 2 dark solitons.
Yes.
And but probably if you can play with the shape of the obstacle, you can observe the formation of states of 3 dark solitons, 4, so on and so forth. Because actually there are states containing many solitons, actually depending on the pump detuning and other parameters.
Well, I think that this is true, but of course, if the realization of situation with even or odd number of solitons will require the different phases in the halves, because overall we must accumulate the phase 0 when we come from the left or the right. So we could potentially observe maybe 4 solitons.
Just a moment. If you have a dark soliton, it means it's not a domain wall. It's each black stripe is actually a bound state of 2 domain walls. Is this correct?
Well, anyway, one soliton is associated with pi phase jump and density dip. So anyway, we have one pi phase jump.
Okay. So you can have only even number of these solitons, but if you play with obstacle, you can have, say, 4 dark solitons.
Probably. It depends on the size of the obstacle. Maybe it will require very fine tuning of the parameters. But even it's thank you very much.
Any final questions? Minor one.
You said the pi stability only occurs like with resonant pumping, or is it also occur by non-resonant pumping?
Well, here all the results were done with the profiting the resonant pump and stability. So all intensities in the phase diagrams and in the soliton hitting the obstacle, we were acting somewhere here, and we were allowed to have the phase either close to minus pi or close to 0, and that's why we were able to observe such a bright, such rich behavior, such rich phase patterns, and everything was done in resonant pump regime.
Okay, In the interest of time, we'll have to conclude here. So let's thank the speaker again.